Hey APBio students, here's your first virtual lecture during these interesting times, and it's going to be on energy and ecosystems. So let's start by just making sure we're all on the same page and talking a little bit about some physics that underlie these energy exchanges within ecosystems. So if we think about the law of conservation of energy, you all know the first one says that energy cannot be created or destroyed, simply transformed or transferred. And that's important to us because we know, therefore, that within ecosystems, the amount of energy stored in organic molecules must equal the total amount of solar energy intercepted by plants, less the amount reflected and dissipated as heat. So that's the biological connection to the physics law. And of course, the second law says that, right, there's this natural tendency towards entropy due to heat being lost in inefficient energy transformations. So we see that in lots of energy transformations within living things, that heat is given off as a waste form of energy. And it's part of the reason why, we're warm-blooded, so that works out well. But it also means that we need a constant input of energy because it's not going to be cycling like when we talked about the biogeochemical cycles of matter, but rather it's going to come in and it's going to flow out because ultimately it ends up out in the atmosphere and into the universe as that waste heat. So that also brings us to the physics connection of conservation of mass. Again, nothing new here for most of you, but this idea that same thing, we don't create it or destroy it. So in this case, though, we're not going to lose it in any kind of transformation in the form of heat that can escape out into the universe. Instead, mass is going to remain on the planet, mostly within ecosystems, although we'll touch back on that in terms of inputs and outputs. So because of the fact that these ecosystems are in fact open systems and not closed systems, we may actually have a loss of matter if things get carried away. For example, wind and water might carry some matter out of one ecosystem and of course deposit it in another ecosystem. So in that sense, we see this loss and gain of matter, but not within the biosphere. So that's a little bit different than the energy transformations. And one of the things that may be impacting the natural balance of these things, of course, is human interference. So human activities may disrupt the balance of some of these cycles that we have talked about and that we'll talk about again in the future. So in this topic, we're really focused on primary production. This is going to be the amount of light energy converted to chemical energy in the form of organic compounds by autotrophs. We're typically talking about plants, but we could be talking about cyanobacteria if we're talking about marine ecosystems during any given period of time within an ecosystem. Kind of just interesting little stat in terms of thinking about what does this really look like for the planet. Earth's atmosphere is going to get bombarded with about 10 to the 22nd joules of solar radiation per day, but we ends up only converting just a very small amount of that into chemical energy in the form of essentially sugar molecules in one way or another. So less than 1% of that energy is actually ultimately captured by autotrophs in ecosystems. So you guys have heard, we've talked previously about net and gross primary productivity, GPP, of course, being the total primary production within an ecosystem, whereas the net primary productivity is going to be that GPP minus the autotrophic respiration, which we represent with the R subscript A. Typically speaking, net primary productivity is going to be about 1/2 GPP. So that's just an average, but that's a good thing to stock away in your head for exams. And it's important because it represents the amount of stored chemical energy that would be available to consumers at the next trophic levels above those producers. We can express NPP in two ways. One is as energy per unit area per unit time, but another way that we can express it is as the biomass added, not the biomass, but the biomass added to an ecosystem's per unit of area per unit of time. So just watch out for which way it's being presented. Some of the most productive ecosystems in the biosphere are going to be tropical rainforests. Again, not a particular surprise, I don't think, to you guys because of the temperature, that is to say warm, and the high levels of moisture. A lot of the abiotic factors for growth and reproduction are met, keeping a constant movement of those biogeochemical cycles as a result of all of that growth of autotrophs and then the consumers. Estuaries and coral reefs are also incredibly productive ecosystems, but they represent just 1/10 of the area that tropical rainforests represent on Earth, that their overall contribution in terms of productivity is much smaller. So it depends on whether you're looking at their overall contribution or their ability to produce are going to give you different relative scales. Oceans, interestingly enough, are relatively speaking not particularly productive. But they're so large that because of their scale and size, they contribute as much NPP as basically all of the terrestrial systems combined. So that just goes to show the important role of cyanobacteria and other photosynthetic organisms in marine environments in terms of contributing net primary productivity, and you could also think about in terms of oxygen contributed to the atmosphere. Another thing we have is net ecosystem production, not to be confused with NPP. So now we have NEP, which is going to be the measure of the total biomass accumulation per unit of time. And it will account for the respiration of all organisms in an ecosystem. And our formula for NEP here is going to be equal to the GPP minus the total respiration, or R subscript T. The results of this equation will let us know whether or not carbon is being lost or gained within that particular ecosystem. So again, you want to think about ecosystem inputs and outputs is the connection there. And also think about the carbon cycle as a biogeochemical cycle and whether or not carbon is being lost or gained in that particular ecosystem. The way that we can measure carbon is going to be by measuring or determining the flow of either oxygen or CO2 that's entering or leaving an ecosystem. When we talk about terrestrial ecosystems, we're typically going to measure CO2. It's an easier thing for us to measure because there's less of it. Oxygen in the atmosphere makes it that much more challenging for us to measure the flow in and out. In an aquatic system, we might opt to look at dissolved oxygen and that flow of oxygen in and out of that system to determine NEP overall. Some factors that might influence net primary production. In aquatic ecosystems, your two big ones are going to be light and nutrients. Obviously, as you move down in water depth, you're going to lose light quite quickly. And then also nitrogen and phosphorus are typically limiting nutrients in those systems. In terrestrial ecosystems, light and nutrients are still going to be important, but we're going to be more interested in, and NPP will be more influenced by temperature and moisture, as evident in my previous example of tropical rainforests being highly productive. So again, nutrients are going to play an important role in terrestrial ecosystems. And if you think about agricultural fields, and if you think of them as like a micro ecosystem or a special ecosystem, then nutrients are going to play a particularly interesting role. And that's something that you can think about. We also can't ignore the concept of secondary production. So secondary production is the amount of chemical energy in consumers' food that is converted to their own new biomass during a given period of time. So we've been talking about what are autotrophs or producers doing. Now we're interested in what are consumers doing when we look at secondary production. And it probably is obvious to you if you think on it, but only a small portion of plant material is going to be consumed. And even of what is consumed, only a small portion of that is actually digested. Think roughage and fiber, right? Animals are not the best at digesting cellulose. Most of us are not able to do it unless we have some kind of symbiotic relationship with, gut bacteria or some other kind of organism that helps us to break down those materials. Think, cows, for example. Termites would be another example. So we can also investigate production efficiency. This is the measure of the efficiency of animals as energy transformers. And the short answer to this question really is that we're not particularly good or efficient at transforming energy, but there is some significant variation across organisms. And this equation, production efficiency equals net secondary production over assimilation of primary production, make it a percent by timesing it by 100, will give us the answer of how well we transform energy. If we look at net secondary energy, net secondary energy will be equal to the energy stored in biomass, represented by growth and reproduction, whereas the assimilation is going to be the total energy taken in, and of course, PE being the percent energy stored in assimilated food that's not used for respiration. And it's kind of interesting what we see if we run this equation on a variety of organisms, and you can see that birds and mammals are really not very efficient. We're looking at a 1 to 3% efficiency rate. Fish, on the other hand, are increasing that efficiency up around 10%. They are ectotherms. That may play a significant role in it. But who really wins the award here are the insects and the microbes, where they demonstrate an efficiency of 40% or greater. So that's some of the variety that you might see across organisms if you run this equation. If we look at trophic efficiencies, this is the percent production that's transferred from one trophic level up to the next. We're going to see that they are always less than the production efficiencies because they take into account three big things. One is the energy lost through respiration. The second is going to be the energy that's still in feces that wasn't taken advantage of because of the inability to digest plant products. And the third is going to be the energy and organic materials in the lower trophic level that weren't even consumed by the next trophic level. We're going to see a range of trophic efficiencies. We typically teach it as 10% is what moves from one trophic level to the next, but it can actually range from anywhere from 5 to 20% when you think about comparing ecosystems or biomes like a desert biome versus a tundra versus a tropical rainforest or temperate forest. You're going to see very different levels of trophic efficiencies. And of course, that efficiency moving from one trophic level to the next is going to very much dictate the length of food chains that we're going to see, typically limiting them to just 4 or 5 trophic levels. And sometimes they're limited to just 3. So it's not a rule it has to be 4 or 5. But once there's not enough energy, then you can't support any consumers beyond that level. And that's it for this. Obviously, I went through this quickly. The power of the video is you can press pause anytime you want. And I would highly recommend that if you haven't already, that you go back and you create a set of notes using this video and then use your book to kind of add in some additional detail. All right, guys, enjoy the rest of your day.